Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. So, we are talking about various examples, how to control degrees of freedom, and we have talked about different connections, different devices we can say, having different constraints and degrees of freedom. So, let us continue. So, what we see here, we have one DOF, which is the rotation here. So, this is what we want. So, and this is your degree of freedom. So, what we realized that okay, DOF is 1. So, of course, then we have to provide 5 constraints, 6 minus 1 equal to 5. So, 5 constraints we have to provide, and since we are talking about this rotation. So, call it x y. So, suppose if I define the axis x, y and z, z axis. So, yes, what we can say is what is desired is the rotation along x axis, and one way we can always show with the rotation, or we can use double arrows what we have here. So, 5 constraints, what are those? So, 3 translations we have to constrain and 2 rotation along y and z axis. So, what we realize that if you can just name it this articulated links. So, say C1, C2 and C3, and on the other side you have C4 and C5. So, if we just talk about C1, C2 and C3 together, what we discuss and what we also see from the configuration here. So, they will locate the point. It means the translation, all the translations are constrained. So, if you just want to give translation to the orange body, so x, y and z, it will be constrained by C1, C2 and C3. Of course, we have C4 and C5 also, but okay, just if we just consider C1, C2 and C3, they already constrain the all the 3 translations. What about the rotation? So, we want to, so we talk about this translation and this translation is a constraint. Now, talking about this rotational constraint, call it RC. So, we want to have that rotation constraint. So, if with C3, if we put C5, so C3 and C5 together, so they are parallel in a plane perpendicular to the y axis, parallel, and there is an offset. So, then we realize that C3, C5 together, it will constrain the rotation along y axis. Now, if we talk about rotational constraint along z axis, so we have to check the plane. So, perpendicular to the plane, and now if we consider C2 and C4 together, what we realize that okay, it makes a plane perpendicular to z axis, and so therefore, if we have C2, C4 with an offset, that will constrain the rotation along the z axis. So, this one will provide all the 3 translational constants, and these together will give 2 rotational constraints, and together we will have 5 constraints except the rotation along the axis, which is desired here. So, likewise, any design, if any configuration, if you want to have depending on the requirement, just by placing these articulated links, and later we call it wire flexures. So, we can replace it with the wire flexures, or we can also think of constraint lines. So, if it's just a contact, then we can establish the constraint lines along those directions, and if you proceed similarly, what we realize that we can get any configuration with the desired degree of freedom and constraints. So, there are other methods, and it's more like we can say it's an artifact, it's embedded in the element in the design itself. So, when we talk about the some of the sections which are torsionally compliant, they can be used to also get a rotational degree of freedom. So, for instance, here this cross section, this is L shape. So, it's a open section, and any kind of if this section, if we take and if we try to just twist it, they are torsionally compliant members. So, if we use these kind of members, we can also get rotational degree of freedom, and that is what we see here. So, if we just weld a orange part to that L section, we can easily twist. There is another embodiment here, and here is like 2 are there and very difficult to visualize, but is along the seam, and but basically is a symmetric design, and we have 2 L welded together to get these kind of pivots. So, it will also provide rotational degree of freedom. All other DOPs are constrained except that the rotational degree of freedom along the axis. So, moving on, what we realize that some of the designs are very simple, and we can use a very simple artifacts or elements. So, not just the articulated links, but we can also use sheets, which we later refer to as a sheet flexures or leaf spring we call it, but yeah, some people may confuse it when we say leaf spring. So, let us better use the term sheet flexures. So, it is just a sheet, plain sheet with the thickness is very small compared to the other dimensions. So, this is the thickness we are talking about, the T. T is really a small compared to the, this is the length, and this is the width. So, the thickness is much smaller, and what we realize and what we discussed earlier also, that whenever we consider this kind of sheet flexures or leaf spring, so it is a planar element. If we take, is equivalent to 3 constraints. So, 2 parallel and 1 diagonal element, and that is how it can provide us 3 constraints and 3 degrees of freedom. What happens if we put in this fashion 2 of them? So, 1 and 2 crossing each other. So, this is what we find. If we see the try to visualize it and see the orthogonal views, this is what we will find from this direction. This is what we see, the cross we see, but yeah, they are like, they are not crossing each other, but they are arranged side by side. And what we realize, if we try to twist, try to give that kind of rotation, it will have rotational degree of freedom. So maybe initially here, but it may not stay here, and there will be slight deviation. There will be excursion. So that rotational axis will move, but if it's for very small range of motion, what we realize that it's a very good design and it can solve many of the problems related to friction. So, we will be discussing this element, this flexure design in detail later when we talk about compliant mechanisms. So, moving on. So, yes, we talk about 5 degrees of freedom, then 4 degrees of freedom systems, 3, 2, 1, and when we constrain all of them. So, constraining all 6 stuff, what we get is the kinematic mount or kinematic clamp. And again we can use the same technique and we can just name it also. So, there can be various ways to explain. So, one of the way is, again we go by C1, C2 and C3. So, C1, C2, C3, they will provide 3 constraints, all the 3 translation constraints. And if you now want to constrain the rotation parts, so these translation constraints all can be achieved with C1, C2 and C3. Moment you want to have the rotational constraints, we want to provide another constraint parallel to one of these C1, C2 and C3, but perpendicular to the axis. So, for instance, if we are targeting this one, this rotation. So, the perpendicular plane. So, if this is the rotation axis, if we want to constrain, so this plane we have to talk about, and if you want to consider that, what we see that C4. So, C3 and C4, C3 and C4 together will constrain that rotation. Similarly, if you want to constrain this rotation, so we can name it, but anyway. So, if you want to constrain that rotation, so what will happen? C4 and we can say C5, they are perpendicular to that plane, that axis. So, the plane perpendicular to that axis, or what we can say the normal, they should coincide, and then C4 and C5 will constrain that rotation. So, this is C4 and C5. So, we are left with now this rotation, the z axis, and in this case if we try to look at it closely, so we have to find 2 constraints parallel and in the plane perpendicular to that normal, right. So, what we see, we can, this is left C6. So, C1 and C6 actually provide that rotational constraints. So, in a way what we realize that all of the constraints are used once, and that way we can get all the 6 constraints and we can design a kinematic mount. So, we can again use constraint line approach, we can place the constraint lines along all the C1, C2 till C6, and what we realize that we can achieve that. Later we will be also talking about equivalent designs, equivalent configurations, and at the conceptual stage what we realize that many of the configurations are equivalent and it does not matter where is the place. So, for instance, in this case C6 can be placed on the other side also. So, again it is equivalent and it does not change anything if it is moved here. Likewise, we can do many such configurations. So, C2 can be placed on the other side. Similarly, C3, C4, C5, some can go on the top also. Yes, what will change is the nature of the forces. So, if we move to the other side, it will be, if it is in tension, if it moves to the other side, it will be under compression. So, that will change. So, there is no one solution, but there can be many solutions, but this is the approach, and then we can try to find different equivalent designs, and sometimes we can also replace with these kind of artifacts. So, like C1, C2, C3, we know that is like a ball joint. So, we can also have this. So, moment we tag one spot, we realize that location is defined and now it cannot move, we cannot give pure translation. And when we consider, so this is equivalent to C1, C2 and C3 all together combined, we will get that spherical joint. If we talk about C4, C5 and C6, is nothing but a planar constraint. So, a sheet flexures can be used in that case, and then we can get the equivalent design. So, that way we can just play and can get many designs, and we can. So, depending on the requirement, depending on the constraints what we have, so there can be a space constraint, we cannot place things the way we want. So, we may have to find alternate solutions, and I think this approach gives us many solutions, and we can explore different alternatives, and we can also look for some kind of optimization based on the boundaries we have. We can also use different kind of artifacts. So, for instance, we can use sheet flexure with the hole. So, and what we understood that it constrains the two translations. So, in this case, if we place like this, so 2C and 2C here, again we are getting 6 constraint, and we can analyze it, and then we realize that all the 3 translation and the 3 rotations are constrained. Of course, the orientation. So, what you see, if I just say is element 1, 2 and 3, 1 and 3 are parallel, but 1 has to be, so element 2 is not in the same plane. If it is in the same plane, what will happen is over constraint, because if you try to move, all will flex, all will bend, and then it will not restrict that motion. So, it is a then over constraint design. But if we put in this way, what we realize that we can always get resolved into two translation constraints, and then it is like 6 constraints as we see in V grooves design, and we can get a very good solution, and is used in many cases wherever we want to design a mount for any precision application or precision instrument, we can go for this kind of design. Now, the question is, each sheet flexures provide 3 constants. So, 3 plus 3 is a 6. So, one can say there are 6 constraints. So, is it possible to constrain all the 6 degrees of freedom using 2 sheet flexures? Any 2 sheet flexures if we take, is it possible to constrain all 6 degrees of freedom? So, yes, we can always resolve into 3 constraints here and try to find the equivalent, and we can check ourselves also whether it's possible or whether it's a over constraint design. Over constraint design means certain degrees of freedom still free and some directions constrained twice. So, if we try to visualize, yes, we can always can have a 3 equivalent. So, for instance, if we want to, for this case, what are the equivalents? 2 parallel you can have and 1 like this. So, if we define some axis, so say x, y and z axis, if we define, yes, these are along the x axis, but yeah, this is making a plane, yes. If we take this, what we realize that is equivalent to 2 constraints in the plane and 1 constraint along this line. So, we can name it also C1, C2, C3, C4, C5, C6. So, one plane, another plane. So, this is the horizontal plane and this is for the vertical plane. From here also what we realize that if we try to twist along this axis, actually this set can be twisted, but the set 2 can be also twisted. It means the rotation along that dotted line is not constrained. And why is so? So, what we also realize that the constraint along that line, there are too many C1, C3 and C6, they are all along the same line. So, what we also realize that along the x axis we have many constraints, and even if we remove one, that may not make any difference. So, it means there is over constraint here, and if we try to see it closely, what we realize that dotted line is nothing but is the intersection of the 2 planes. So, if we talk about the 2 planes 1 and 2, so 2 sheet flexure if we take and if we extend, wherever they cross or wherever they intersect, so 2 plane always intersect at and they will give us a line, and that will be the over constraint direction, and that is the axis of rotation which we will always have. So, it is a over constraint design, and that is what we see here. Okay, translation is over constraint and rotation is free along that line. So, always remember with the 2 sheet flexures cannot provide 6 constraints. It only provides 5 constraints, and there will be always 1 degree of freedom, which is the rotational degree of freedom there. And it is an exercise for everyone to try, no matter how you place them, even parallel it is, even if you take a parallel sheet flexures, you will find that there will be a rotation, and wherever they intersect it will rotate at that point. So, if we take a sheet flexures like this, so if we take these two planes, what will happen? I think we can just extend, and wherever these two planes intersect, there will be rotation, and what we realize that when it is a parallel, it is going towards the infinity, and if you rotate at along that axis, what we get is the translation. So, we will get a straight guidance system. So, you can try, you can take any configuration, two planes you take and try to visualize. You can even try with the simple, you can take two pieces of paper or any visiting card you have, you try to clamp it or glue it and try to observe. It will be a fun experiment, but you will get very nice insight, and probably you will feel confident to use them. So, we will be talking about more such designs later when we talk about the compliant mechanisms, but you can just see here also that how it works. So, if you want to have exact constraint design, can always remove one of the constraint, and now you can say 3C and 2C. So, total 5 constraints, and you have one DOF, which is the rotation. So, if you just consider two sheet flexures is our constraint design, and if you want the exact constraint version of that, one of the sheet flexures you have to use, and then other one you use with the whole. So, some more examples we can use, and how we can control different degrees of freedom. So, this is from my PhD work, and what we wanted to have is exact constant 6 DOF force measurement. So, in a way it is a 6 DOF force measurement device, or you can even call it load cell, or many times it is also referred to as reaction platforms, but it can be designed as per our requirement, and we do not have to buy very expensive load cells, 6 DOF load cells, multi axis load cells, but we can just use the concept and can design our own platform, our reaction platform. So, how is done? Again we use the constraint line approach here, and we can use the what we just discussed 3 plus 2 configuration. So, we can locate the point and then constrain the 2 rotation or the 3 rotation, 3 plus 2 plus 1, or we can also go by 2 plus 2 plus 2. Here I use 3 C's the bottom. So, you constrain it in the plane, and then you provide another 2 and plus 1, 3 plus 2 plus 1, that is what many times is referred to, and that is how we can constrain all the 6 degrees of freedom, 3 translation and 3 rotations. So, it is we can replace the constraint line with the articulated link, and later it can be also replaced with the wire flexures. what we have here. So, this is the concept and embodiment design here, and yeah, if this is the detailed design where we have the load cell here, this is the your mainly the member which is like providing the one DOF constraint, one constraint, and this is the some mechanism to protect and preload it. So, you can always refer to this article and you will understand about this. And what we also realized that if it's exact constraint design, then we should be able to write the forces measured by the load cells and always convert into the forces in the XYZ and the torque along XYZ directions. So, and that is what we say, there is 1-to-1 correspondence whenever there is a exact constraint design. And for instance, if we just try to look at it, what we realize if we are talking about Fx, so Fx is this direction. So, if the force in x direction is applied, what will happen? So, 1, 2, 3 and 6. What we realize, if we apply force Fx, the constraint provided by 1, 2, 3 and 6, they will not provide any constraint, because the motion, because of the force Fx, whatever infinitesimal displacement what we are talking about, is normal to the constraint lines 1, 2, 3 and 6. So, the entire force, so what we will receive is the force along 4 and 5, the reaction forces. And what we see here, since it is compressive in nature, so what notation we have used is negative sign for the compression and positive sign for the tensile forces. So, what we realize that Fx can be written as simply minus F4 minus F5, and this is what you see if you try to just, so all zeros except F4 and F5. So, likewise we can write Fx, for instance, if I want to write Fy. So, if I apply a force along this direction, Fy, it will be only constrained by the constraint 6, again is a negative, is a compressive in nature, and that is why if we talk about Fy, what we see here is only minus F5. Likewise, you can write and then convert into matrix form, and then very simple notation. So, Fx is the force vector comprising of Fx, Fy, all the components, 6 component. So, whenever we say force, it also includes the moments or the torques, and here Fn is the forces measured by the load cells, and A is the matrix, and is basically because of the geometry, whatever configuration which is choose, accordingly this will be, this is what we get. So, what we can see, you can start with the very simple concept about the application. Suppose we wanted to build this force sensing device, and this is the platform where we mount this flexible tube. So, it is for medical application, and what we wanted to have, if we insert an instrument through this and try to interact, or if it interacts with the tube, what kind of forces will be there. So, translation and rotation what we are talking about, and then can we measure it, and this we can just put on top of this blue platform, and any force we can easily measure. So, this can be designed, and this is what I have. So, this is the actuation unit, and this is the again for sensing to measure the rotation and the translation, and we use a very nice concept here. Again, it is a contactless. Here is a supported on air bearing, so it can translate very easily. And then this is the tube what we have is mounted on this platform, which is supported on 6 wire flexures. So, and it is not very big, it is just 1 millimeter diameter, and I think it is about 30 millimeter length, and 6, and it can take a very good load. Of course, if it comes under compression, we have to be aware of the buckling load, the critical buckling load, but if we are able to design it in a way that all the forces are in tension, we can imagine that if we take a steel wire of 1 millimeter diameter and of a length suppose 20-30 millimeter, we can do the calculation and we can check the load bearing capacity, and even the stiffness can be very high because it is a EA by L. So, it is all the axial stiffness we are talking about. So, this is a small video what we have here. So, what you see here is a cam, and we are using 2 laser displacement sensors. So, it can measure the travel as well as the rotation. So, and it is supported on air bearings, and it is a glass tube. So, the instrument is inserted, and as it rotates it comes in contact with the glass tube. So, we can see the actuation platform, and it does both the translation and the rotation, and we can measure the reaction forces very precisely. So, there are similar examples, and we can use the constraint line approach again. So, what we see here is a huge display, and it was installed in one of the shopping mall here in Delhi. So, I just clicked it and use it for the course, and what we realize here, we can see the cables here, 3, then you have here 4, 5 and 6. So, C1, C2, C3, C4, C5, C6, and very good exercise. I think we can also highlight it. So, again C1, C2, C3, this might be connected to the other side somewhere there, somewhere here. What you realize that these cables are anchored on the 2 sides of that open space, and it is a very circular shape. So, at the bottom is connected to this thing, and the configuration is such that it constrains all 6 degrees of freedom. There will be a special configuration where it may not provide all the 6 constraints. So, and that is, it should not, all the constraints should not meet at one point. So, what happens if all of them are like intersecting at one point, and suppose it's placed here 3, 4, 5, 6. If you try to rotate the object, you cannot constrain that rotation. So, it's a over constrained design. It means it's a no. So, it should be done differently, and I think it was nicely done. And the nesting force here is mainly the weight of that the entire thing. So, it was there for many years. I am not sure why it was removed, because I do not see any problem in this design, but I do not see this screen anymore there. So, either somebody was, maybe they were afraid that it may fall, but if you understand the concept, if you understand the exact constraint design, you know that it is not going to fall and it will constrain all degrees of freedom. And since it is very heavy, so all the cables or the ropes will be under tension. So, no need to worry. So, even a small disturbances in x, y and z direction, it will not give any problem. Yes, what you see later, like the subsequent portions, they are suspended with the 3 cables only. So, of course, that has to be analyzed, and you may realize that the lower one basically not constrained, because 3 will only provide 3 constraints, and so that, but top one definitely constrained with sufficient force, and you have 6 constraints, 6 cables. So, it will provide all the constraints. So, very nice example, and one can always think about it. You can always draw a parallel between these kind of. So, any cable if you take, as long as it's in tension, it will work. So, now any design using cables, even the big cranes for moving the materials, and if you want to avoid any kind of sway, and suppose want the material to move very fast and working on high rise buildings, and they are all using steel cables. And what do you realize, that you can, using proper controller strategy and the sufficient number of cables, you can manipulate the object precisely, and you can go at a very high speed, and this is also one area of research many people work on. But the basis is the constraint using the wires. So, we will take some more examples. So, for instance, if we are talking about ball hinge, what we have here. So, it's based on contact, and so the friction is there, and many times it will give rise to problem and will have a hysteresis, and very difficult to position it. So, of course, if it's for a small range of motion, or if you want to find an equivalent using wire flexures or with the wire or cables, we can always use in the 3 perpendicular axis. Of course, here it will be little offset, because means they cannot cross each other, otherwise the properties will change. So, they have to pass and they have to go side by side. So, the pole, we cannot get the exact pole, but slightly off, but for many application it is a good, and the offset we can always measure with respect to the rotation. and we can always compensate for that. So, this is using simple wires, maybe 1 millimeter, 0.5 millimeter wire, steel wire with the 20 millimeter or 30 millimeter kind of length may be sufficient for many applications. So, let us stop here. We will continue with the more examples talking about different kind of coupling and how we can constrain, provide a rotational constraint. So, there are practical examples which has been used earlier, and unknowingly we are also using it, but if we understand the science behind it and if we understand the constraint concept, I think we will be able to design with the very simple artifacts. We can develop different kind of design and we will be able to use them. Thank you.